Imagine building something with Lego bricks. The final creation, whether it's a castle or a spaceship, gets its properties from how you arrange the individual bricks. Now think about materials. We usually think of materials like wood or glass having fixed properties. But what if we could build a material from tiny, artificial atoms, structures much smaller than the wavelength of light or sound? That's the big idea behind metamaterials. They are engineered materials whose properties come from their structure, not just the stuff they're made of. It's science. And it allows us to do things that are just not possible with materials found in nature. So where does the nonlinear part come in? Well, in most materials, if you double the energy you put in, you get double the effect out. That's a linear relationship. It's predictable. But nonlinear metamaterials are different. They don't follow such simple rules. When you send a wave, like a beam of light, into them, their properties actually change based on the intensity of that wave. A weak light beam might see one thing, but a powerful light beam sees something completely different. This opens up a whole new world of possibilities for controlling energy in ways that were once just science fiction. This special behavior isn't just a small tweak, it's a game changer. Think of it like a secret door that only opens when you push with just the right amount of force. For these materials, the force is the intensity of light, sound, or an electrical signal. This nonlinearity allows scientists to manipulate waves with incredible precision. We can bend light in unusual ways, focus sound into a tiny spot, or even make an object invisible to certain frequencies. It's all about designing those tiny building blocks, the meta-atoms, to respond in a very specific, nonlinear way to the energy passing through them. The real magic happens because these materials are designed, not discovered. Scientists use computers to figure out the exact shape, size, and spacing of the tiny components. These could be little metal rings, wires, or other complex shapes, arranged in a repeating pattern. This careful design is what gives the material its superpowers. It's not the metal or plastic itself that's special, but the structure. By controlling the structure, we control how the material interacts with energy, especially when that interaction depends on how strong the energy is. It's a whole new frontier of engineering on a very, very small scale. One of the coolest tricks of nonlinear metamaterials is their ability to switch between different states. It's like a light switch, but for the properties of a material. Imagine a material that is transparent to a weak light beam, but suddenly becomes opaque or reflective when the light gets brighter. This is called optical bistability. The material can exist in two stable states for the same input, and a small change in power can make it flip from one state to the other. This happens because the intense light changes the material's internal structure just enough to alter how it interacts with the light itself. It's a self-regulating feedback loop. This isn't just a random effect. We can actively tune it. Scientists can embed tiny electronic circuits or use materials that change shape with temperature or electricity. By applying a voltage, we can change the properties of the meta-atoms on the fly. This gives us real-time control. We could have a lens that changes its focus with the push of a button, or an antenna that can be reconfigured to send or receive different signals instantly. This tunability means we can create adaptable devices that respond to their environment or to our commands, which is incredibly useful for all sorts of technologies. Sometimes these materials do things that seem to defy common sense. For instance, self-action effects are where a wave changes the very medium it's traveling through. A powerful laser beam can create its own tunnel or lens inside a nonlinear metamaterial, focusing itself into an even more intense beam or guiding itself around corners. This is because the strong electric field of the light rearranges the particles in the material, which in turn alters the path of the light. It's a bit like how a bowling ball makes a dip in a trampoline, affecting how any other marbles on the surface would roll. These powerful interactions are what make nonlinear metamaterials so exciting. They give us a new set of tools to control energy. Instead of just passively guiding a wave, we can make the wave itself an active participant in its journey. The wave's own power becomes a control knob. This level of control, where a material's response is dynamic and depends on the intensity of the signal, allows for creating smart devices that can process information, protect sensors from damage by strong signals, or create new pathways for energy to flow in previously impossible ways. Consider the possibilities. Let's talk about color. The color of light is determined by its frequency. In everyday life, a red laser beam stays red. But in a nonlinear metamaterial, things get weird. In a good way. This is where frequency conversion comes in. You can shine two different laser beams, say a red one and a blue one, into the material. And what comes out can be a completely new color, like green or even ultraviolet light. The material acts like a mixer, combining the frequencies of the incoming waves to generate new ones. This is called harmonic generation or frequency mixing, and it's a powerhouse tool in physics. Why does this matter? Well, creating certain frequencies of light, especially in the ultraviolet or terahertz range, can be very difficult and expensive with conventional technology. Nonlinear metamaterials offer a more efficient and compact way to do it. You can take a common, cheap laser and use a metamaterial to convert its light into a much more specialized frequency. This is huge for things like medical imaging, high-speed communications, and detecting dangerous chemicals, all of which rely on having access to specific frequencies of light. It's like having a universal remote for the electromagnetic spectrum. Now let's get to solitons. Imagine a wave pulse in water. As it travels, it tends to spread out and lose its shape. But a soliton is a special kind of wave packet that holds its shape and travels over long distances without dispersing. Nonlinear metamaterials are fantastic at creating and guiding solitons. The nonlinearity of the material counteracts the natural tendency of the wave to spread out. The intense part of the wave travels a bit differently than the weaker parts, and this effect perfectly balances out the dispersion, keeping the pulse tightly packed. It's a self-sustaining wave. The existence of solitons and special surface waves known as surface plasmon polaritons is a big deal. These waves are confined to the surface of the metamaterial and can be controlled with amazing precision. Because they are so tightly bound to the surface, they are extremely sensitive to any changes there. This makes them perfect for building ultra-sensitive sensors that could detect a single molecule. By using light to control these surface waves, we can create all optical circuits where light, not electricity, carries information, leading to computers that could be thousands of times faster than what we have today. So, how do we build these amazing things? It all comes down to their discrete nature. The word discrete just means they are made of separate, repeating parts, those meta-atoms we talked about. By carefully designing each tiny element and the space between them, scientists can control the collective behavior of the entire material. It's a bottom-up approach to engineering. This is very different from a natural material, where you're stuck with the atomic arrangement nature gives you. Here, we are the architects deciding exactly how waves should behave. This approach could revolutionize countless technologies. Take lenses, for example. A conventional glass lens is curved and bulky, but a metal lens made from a thin sheet of nonlinear metamaterial could achieve the same focusing power in a device that is flat and thousands of times thinner. And because it's nonlinear, its focus could be changed just by varying the intensity of the light passing through it. This could lead to super compact cameras in our phones with powerful zoom capabilities, or even advanced microscopes that can see things we've never seen before. It's a total reimagining of optics. The potential for new kinds of sensors is also enormous. Because nonlinear metamaterials are so sensitive to changes in their environment, they could be used to detect tiny amounts of a specific chemical or biological agent. A sensor could be designed to change its color or electrical properties dramatically when it comes in contact with a target molecule. This could lead to instant medical diagnoses from a single drop of blood, or real-time environmental monitoring systems that can alert us to pollutants in the air or water with incredible accuracy. Ultimately, nonlinear metamaterials give us an unprecedented level of control over the fundamental forces of our universe: light, sound, and electromagnetism. From tunable devices that adapt on the fly to new forms of energy harvesting and ultra-fast computing, the applications are just beginning to be explored. We are moving from being passive observers of the laws of physics to active participants, bending them to our will. The future will be built with these smart, structured materials, and what we can create is limited only by our imagination. Science is AWESOME.